Good morning, everybody. Today we're going to be starting chapter 24, which is comparing means. So we previously in chapter 23 did confidence intervals and hypothesis testing for one sample t-tests and one sample t-intervals. So as you can imagine, today we're going to be working with two sample when we're doing comparisons. So take a moment to read this problem. And this is going to be the problem we're going to be using throughout the chapter. Okay, so basically they're comparing brand name batteries versus generic batteries. It's actually quite surprising that the generics came out so strong as far as their life is concerned, because I don't know about you, but whenever I bought cheap batteries, they don't last long, ever. On the subway, they used to sell them for $1 for two. So, yeah, back when we used to have Walkman. So this graph is a box plot and doing comparisons. And box plots are super helpful when you're doing comparisons between two different samples. That being said, there's some shortcomings for it. So we can talk about some of the things using CUS and do some comparisons, but there's really one main thing we can't do. Center. We know the center. The center is in this case, median. The median for the brand name one seems to be, I don't know, roughly about 190. The median for the generic seems to be around 205, maybe a little less than that, right? Let's talk about unique later. The spread for the generic is going roughly, what do you say? I want to say 170 to, I don't know, 205. So the difference would be 35, right? So the spread for the first one is 35, while the spread for the generic is going to be from, let's just say 190 to 220, would you say? So that's going to be 1030. Okay. The shape is the part that we can't do. We certainly can talk about skewing. In both cases, it seems like there's mild to no skewing in the brand name, maybe a little bit skewed to the left because there's more data between the median and the lower number. But certainly it seems like there's more, I don't know, it's kind of about the same, maybe a little bit skewed to the right on the generic. So we would talk about skewing, but what we can't talk about is unimodal. When we're dealing with box plots, we cannot talk about it being unimodal. So don't ever talk about the modes when we're talking about box plots unless you have the data and can also talk about it. So what I would suggest, because histograms also have their place, is to potentially do both a box plot and a histogram if you have time and if there is a need for it. Maybe even just quickly doing a box plot and then mentioning the histogram. The histogram will probably give us more information. I also like this because now I can quickly say something to the effect of, also, if we're talking about comparisons, I would like to say that the max of the brand name is equal to the median of the generic. And I would like to say that the min of the generic is equal to the median of the brand name. I mean, that's powerful information. Interesting, right? So when you're talking about comparing and contrasting, don't just make a laundry list. Also use your knowledge to say, wow, this is interesting that the median is actually the max for the brand name. I mean, with all things considered, I would buy the generic. Just really, in this case, no reason to go with the brand name. Okay. So comparing means, we're doing obviously a side-by-side comparison. We're doing the box plot. We're doing the histogram. We always have to look at both. When we are doing the difference, it's going to be mu1 minus mu2. So in the case of this one, I think they're trying to see if the generic, I really don't know. It's so obvious that the generic is going to be better, but maybe you'd say that the mu of the generic minus the mu of the brand name, or vice versa. Okay. So that's what we would do. I like to put the letter of what we're looking at, so that way it's clear. Otherwise, if you do that, what I just did, you don't have to make a let statement. But if not, if you want to do mu1 equals generic and mu2 equals brand name, right? And then I would do mu1 minus mu2 or something like that. Okay. So for independent random quantities, we add variances, even if we're subtracting. So when we're doing the difference, we're subtracting. But when we're doing variances and we're doing standard deviations, we add, always add, right? So we would take the standard deviation, square it, divide it by the number in the sample. In the case of most means, we don't have a population standard deviation, so we have to do standard error. Same thing, standard deviation of the sample squared divided by the number in the sample plus standard deviation of the second one squared divided by the sample. Okay. So I have an example here, kind of fun. So take a moment to watch with me this video, and we're going to do a problem. So let me make it bigger, and let's go. Play. How do we play this thing? Get out of the way.
So here's the second eating myth. What happens if your plate never empties? I mean, would you just keep eating like the family dog until we blew up? Well, we designed this refillable soup bowl. And this is an actual restaurant. And this woman here, what we did is we took soup bowls, drilled holes in the bottom, drilled holes through those tables, and then strung food-grade tubing to the bottom of the bowl, through the table, into these big cauldrons of soup. Okay, there's 6 quarts in that cauldron, and as this woman eats, the level in that soup bowl is going to imperceptibly start to drop. When she stops eating, it's imperceptibly going to start rising again. Okay, to the point that she's going to have to finish 6 quarts of soup before she sees the bottom of that bowl. Yeah, I know, that's terrible. Oh, but now, how many of you, if you're eating from bottomless bowl for 10 minutes, know something is going on? Well, we all would, because we're all smarter than a bowl. Remember that? But about 180 people that we did this with, guess how many figured something was going on? Oh yeah, exactly right, 2. One guy dropped a napkin, went to pick it up. Yeah, and there's all this Borg-like tubing underneath it. And this other person, I think, getting that he wasn't at like a Viking feast, grabs the bowl and pulls it like this. I mean, this is pressure-fed soup. It hit the side of his chin. Sort of, the woman next to him went, ah! and the guy across the table stood up so fast he knocked his chair over. So yeah, we had to have a conference to figure whether we were going to get rid of that date or not. But we did. Well, one of the things we find is here's the soup, what the table looks like. You can see all these. Looks like you got these levers. Looks like you're like a U571 or something when you change the valves. One of the things we found is that the typical person who's eating out of a bottomless soup bowl ended up eating about 73% more soup. Okay, but when we ask them, "Wow, are you full?" They go, "No, I mean, how can I be full? I still have half a bowl of soup left." And we eat with our eyes and not with our stomach.
Okay, so why did I show you that video? Besides the fact that guy's kind of, should we say nerdy? Because this actually was a true experiment done to see whether people will in fact eat more with a bottomless bowl of soup. And you're like, how did we do it? Well, here's actually how we did it. So there's a question in the book, and we're going to go through it right now. And we're going to use it again throughout the chapter. But we have over on the right the number of ordinary bowls and the refilling bowls. We had 27 people in each. And the amount they ate was 8.5 ounces in the ordinary bowl and 14.7 ounces in the refilling bowl. So we have our standard deviations there. How much variability do we expect in the difference between the two means? I could just ask you that, and you have to know variability is standard deviation. But it was nice of them to say, find the standard error. So I want you all to start thinking of words that you might see and say, variability. I'm going to talk about standard deviation. How do we expect in the difference between the means? But remember, for difference, we're going to be doing the standard deviation of the first one over n plus the standard deviation of the second one squared over n2 and all over under the square root. So let's do that math right now. So we're going to do second quit. Get out of this. Follow along with me, please. Second quit. Okay, so we're going to do the square root. Oh, I should put it over here so we can see the board. Okay, the square root, second square root. The first bowl was a 6.1 squared divided by the number in the sample, which was 27. And again, 27 people had the ordinary bowl, 27 people had the refilling bowl. It just happens to be the same number. It didn't have to be. Plus 8.4 was my standard deviation squared for the second sample of the refilling bowl divided by 27. So how much do we expect? We have 1.998 is our standard deviation. Okay? And in fact, that's standard error. Okay? Fine. So why don't we try an example using the batteries. So how much variability do you expect between the two means? I'm going to do the math using my calculator this time. I'm going to have it do the math for me for the stat edit, and I'm going to put in the data. So let's do L1 will be my brand name. Let me put that in. Follow along, please, if you're able to. 0.4. 184 and 169.5. So you can see there's going to be reasons why I'm going to use stat edit, and there's going to be reasons why I don't have to, like the example with the bowl. 190.7 for the generic, 203.5, again 203.5, 206.5, 203.5, 206.5, 222.5, wow, that lasted a long time, and 209.4. Okay, so to find the standard error for each of them, I'm going to do stat, calc, 1var stat. My frequency list for the first one for the brand name is going to be L1. And you know what I'm going to do? I'm going to write two things down. I'm going to write down the X bar, which is 187.4. And I'm going to write down my standard deviation. Remember, it's sample, which is 14.6. Okay, that's for brand name. The generic, I'm going to write these two down because I'm sure later on I'm going to need the X bar anyway. I'm going to go back to stat. I'm going to go to calc, 1var stat. I'm going to change it to L2 this time. So that way I can then do no frequency list here in this example. And I get an X bar of 206 and a standard deviation of 10.3. So in this case, my X bar is 206 and my standard deviation was 10.3. So the question is, how much variability do we expect between the two means, between the difference between them? So let's do the math. So we have 2, 4, 6 numbers in each. So I'm going to do, for the brand name, it doesn't matter the order, 14.6 squared over 6 things plus 10.3 squared over 6 things, all under the square root. And again, I'm going to go here. I'm going to go second. And I'm going to do 14, oopsie, 0.6 squared divided by 6 plus 10.3 squared divided by 6. And I'm going to hit enter. And the variability I'm seeing, the difference between them is 7.3. So the standard error would be 7.3 between the difference. Okay, not so bad, right? So comparing two means, because we're working with means and estimating the standard error of their differences using the data, we shouldn't be surprised that the sampling model is the student t. The confidence interval we build is called a two-sample t-interval, differences in means, and the corresponding hypothesis test is called a two-sample t-test. The data we're going to be using is going to be as follows. We're going to have the, if we're looking for the t-score, right, just like a z-score, we would do the difference between the two samples minus the difference between the mu's, and in this case, it actually is going to probably be 0, right? We're trying to see whether there's any difference, and over the standard error, which we just found. Let's just run through assumptions and conditions for these. The assumptions and conditions are very similar to a combination of the conditions for means and conditions for two proportion. Okay, so we have a random condition. We still need to know whether it's random. Independence is also needed. We'll talk about that in a second. 10% condition says we don't usually check this condition for means. We'll check it for means only if we have a very small population or extremely large sample. In the case of the batteries, 6 is not a small population. There are millions of batteries around, and our sample obviously is not large either. Same thing with the soup. People eating soup is going to be, ultimately not infinite, but millions. And the sample we had was not large. What are they talking about? If it's small or large? 2 months ago, it would have been people with COVID-19, where we had a very small population. Now we have a pretty big population, in large numbers, in the millions, ultimately, globally. So this condition is fine. We wouldn't have to check it. But certainly 2 months ago, or even 3 months ago, when it was just in its infancy, COVID-19, you wouldn't have had a big enough population yet in order to work through it. Okay. So let's keep going. So you don't really have to check the one, but you can mention it. You won't get points off if you do. Nearly normal. That's what we have to talk about. We have to look at it for both of the groups. So we're going to do it for, in this case, with the batteries, the brand name, and the generic. If we're talking about the soup, we're going to be doing it for the bottomless, meaning the refillable one, and the ordinary bowl. Last one is independent groups. The groups we are comparing must be independent of each other. Point being, chapter 25 is going to be if they are not independent. The biggest one where things are not independent are going to be when they're the same person before and after. I'm on a weight regimen for food, and so we'll talk about my weight at the beginning and the weight, 8 weeks later or something like that. That's a before and after. That is not going to be independent. I'm the same person, just with different time frames. So that's kind of a super important thing. So you have to make sure that they're independent. As soon as you see they're not independent, before and after, you know that this is not going to be what you're going to do. You're going to do something different, which we're going to talk about in chapter 25. So let's look at the 2 histograms here for the bottomless soup and the ordinary soup bowls. So we have 27 for ordinary, 27 for the refillable. Can the researchers use their data to make inferences about the role of visual cues in determining how much people eat? So it says it's random. Where is it? Random. Okay, it's random. We can say that the groups are independent of each other. We have ordinary bowl and we have refillable. They're not the same group, right? So that's independent. So I should write these down. Random, independent groups. We don't have to talk about less than 10%, but certainly it is of the population. So let's talk about the nearly normal condition. Is it nearly normal? So the ordinary bowl, right? The ordinary bowl, we have, it's unimodal. And it is skewed slightly. Skewed right. What's wrong with my finger? It's not skewed right. Okay. With a number of 27, which is close to 30, you only need to make sure it's unimodal and skewed a little bit, which it is. The refill is also unimodal, and it is slightly skewed. So I wrote nearly normal. I was going to write a question mark, but I didn't. It is nearly normal, period. Okay. So therefore, the question is, can researchers use the data to make inferences? Yes. All conditions met. Okay. Fabulous, fabulous. And that's it for today. So we'll do another video on Friday. You guys have a wonderful day.